Hi everyone, my name is ASimone. I'm a PhD candidate in petroleum engineering at University of Houston. I'm honored to be working with Dr. Lori Hatton and Dr. Mac Myers, measuring properties in unconventional rocks. I have over 20 years of experience in the oil industry, and I went back to school to get my PhD in petroleum engineering. I'm now doing mostly lab and modeling work, as well as working as an independent consultant. Our research is focused on developing an acoustic velocity model in unconventional reservoirs based on acoustic measurements made at different length scales on several types of unconventional rocks. I'll highlight some of our initial conclusions and talk about what we plan to do next. I would like to start by thanking Metarock's Menir Alden for contributing data and measurements to our research, as well as to Robert Patterson for his help in the design of the experiments using Metarock's triaxial cell with the unique capability of measuring simultaneously vertical as well as 45-degree compressional velocities within a single sample. I'll also like to thank Weatherford's John Beskub, Dipti Settler, and Yibing Zhang for performing acoustic microscope measurements for us. Finally, a great thanks to Peter Gwen for the donation of an acoustic microscope to our lab. I'll structure my talk in three main parts. First, I'll make the case for our research on acoustic velocities in unconventionals, what types of acoustic measurements are available, and what samples have been selected. Then, I'll talk about the measurements with some key observations that will link into the models. Finally, I'll talk about the modeling efforts so far, with some initial conclusions and future work. So why should we measure acoustic velocities in unconventional rocks? Acoustic velocities in unconventionals have been studied for several decades, with an emphasis on detection of hydrocarbon source rock from seismic for exploration, rock mechanics for fracking, and pore pressure prediction for development, and so on. Overall, acoustic data is critical through all the life cycle of the field. But in spite of all the progress made measuring these velocities, we still don't understand the specific acoustic response and elastic properties of the individual constituents that make up the range of unconventional rocks, especially those of kerogen, as well as their key controls. Part of the reason for this is that the measurements are performed at a plug scale, so we're looking at the upscale acoustic response for this specific rock volume. Having said that, progress has been reported using atomic force microscopy to measure elastic moduli on individual components. Along the same lines, acoustic microscopy has been used by Dr. Prasad to generate high-resolution images of individual components in unconventional rocks at different thermal maturities, but mostly on isotropic samples and without quantifying acoustic properties, and I'll mention more on this later. More importantly, shells are inherently complex, showing a preferential particle alignment that results in vertically transverse isotropy, with the axis of symmetry normal to bedding, that is vertical, and isotropic horizontal layers. This means that proper velocity characterization, and consequently the definition of elastic moduli, requires measurements at multiple angles to correctly derive the compliance tensor. In sedimentary rocks, elastic rock properties depend on the individual component properties, that is the grains, the framework, and the pore filling fluids, the relative amount, and the geometry of each component. The combined elements may be modeled as a homogeneous material at length scales larger than the individual constituent minerals and pore fluids. The stage differential effective meter model, which is the focus of our research, is designed to incorporate individual constituent properties into a mix to estimate effective moduli, including percolation thresholds and length scales. The effect of porosity, kerogen content, maturity, and mineral phases on acoustic velocities is quantified and incorporated in the model. We're now going to talk about the types of acoustic velocity measurements and their resolution. As I mentioned before, acoustic velocities are mostly measured at the plug scale on rock samples. Velocity measurements are normally performed isostatically and can either be unconfined or confined, using either a triaxial cell, which can do either measurement type, or using a clamp fitted with acoustic end caps to record the velocities and a load cell to record the pressures. In either case, an actual load has to be applied on the sample to obtain a signal that is strong enough to measure the arrival times. Compressional and shear velocities are recorded continuously at the design stresses and actual loads. On the right, you will see an example of the recorded waveforms with the individual arrivals for one of our samples measured in a triaxial cell. You can see the individual arrivals, including metal rocks, simultaneous integrated P wave measurements mentioned earlier. Here's a P wave, and this is the P wave at the 45 degrees. The peaks are identified at each pressure step, keeping the actual load constant, and then a single velocity response is determined at a representative in situ pressure. Now, if we want to talk about the high-resolution laminar scale acoustic velocity measurements, these are achieved using an acoustic microscope. These are used normally to check electronic parts for defects, so they're not really used to measure rocks. For our research, we're using it to determine velocities at the laminar scale. The acoustic microscope measures the time of flight of the compressional acoustic pulse through the material. The same transducer produces the acoustic pulse and measures the response. So it is similar to a microseismic survey in that it measures a volume of rock. It can be used for imaging by selecting the arrivals at a specific time window and mapping that specific surface, like the one I'm showing here of an Eagle 4 sample that we measured at Weatherford. This is also the way it has been published in literature by Dr. Prasad. But rather than an image, we are focusing on the velocity by calculating the travel time at each individual layer. As seen here, this is a velocity map, and here's a velocity scale. The travel time is picked at the top surface to the back surface of the sample using the time of flight and the thickness. I'm going to talk now about the samples that were selected, their characteristics, and I'm going to focus on the Eagle Ford and Monterey shell samples. To determine controls on acoustic properties, samples were selected to test a range of mineralogy, porosity, total organic carbon, and thermal maturity. The range of selected properties is used to test and quantify the acoustic behavior of load-bearing versus isolated components, which has a key impact on the velocities. The wider research beyond this presentation includes most of the formations shown in this ternary diagram. However, we will focus on the Eagle Ford, Bakken, and Monterey for the portion of the study presented today. Most of the samples included in this research measured 1-inch diameter by 1 to 2 inches in length. Twin sets were cut at 3 different angles to bedding to test acoustic anisotropy. Anytime I refer to a VP0, I'll be meaning normal to bedding, as shown in the far right. For VP90, I will mean parallel to bedding, as shown in the middle plug. And the leftmost plug shows the 45-degree angle to bedding. Now that we know which formations we'll focus on, let's look at some of their characteristics to examine the impact of thermal maturity on the load-bearing components. I'm showing here low and high thermal maturity Eagle Ford samples, thin sections and SEMs, to illustrate the changes in organic matter distribution through maturation. We can see that on the low thermal maturity sample, the organic matter, in this case kerogen, has a bedding plane parallel orientation with somewhat continuous distribution. In this case, the kerogen is a significant load-bearing component and is expected to have a greater impact in the acoustic velocity. For the high thermal maturity sample, the organic matter has changed distribution within the pore system due to the in situ cracking and hydrocarbon expulsion, showing isolated remnants of organic matter and pyrobitumen in interparticle pores that are no longer load-bearing. We can see here the pilloidal mass with the interparticle pores. Here is the pyrobitumen highlighted with the red arrows. Finally, the acoustic impedance maps generated by Dr. Prasad also show the changes in distribution. The white shows the lowest impedance values, corresponding to the organic matter. A connected kerogen network is shown on the left image, and on the right, the remaining organic matter is in the form of isolated organic lenses. These are no longer continuous nor load-bearing and will have a different impact on the velocity. Just like the Eagle 4 samples illustrate the effect of thermal maturity on load-bearing components, the Monterey shell samples show two different impacts: the impact of anisotropy in the velocities, as well as the impact of the low elastic moduli contrast between the matrix and the inclusions. The lack of preferential orientation of organic material due to the thermal maturity results in a very low acoustic anisotropy. This comes from the network of clay-filled fractures, cross-cutting bedding, and the quartz cementation during amorphous silica stabilization, which has created a nearly isotropic material. This results in a low contrast for the moduli between the matrix and inclusions for the organics. We will examine the compressional velocity results next. We will start with some observations of the results leading to the models. Literature measurements from Dr. Werneck, data provided by Meadowrock Laboratories, and other measurements performed by our lab were analyzed and used to generate the models that will be shown next. The compressional velocity versus organic matter content is plotted at the same scale on each plot. On the left plot, we show the Eagleford and backend velocities, and on the right plot, we show the Monterey shell velocities. The data is colored to differentiate the velocity direction to bedding, where red shows parallel to bedding or VP90, and blue shows normal to bedding or VP0. The samples were cut as twins to understand acoustic anisotropy. Each pair plots at the same organic matter content. The first observation is that velocities parallel to bedding are consistently faster than velocities oriented normal to bedding. The velocity separation at each twin pair indicates the degree of acoustic anisotropy. On the Eagleford and backend samples, both groups follow the same velocity trends. The only variation is the organic matter content and mineralogy. The backend are shown as triangles and Eagleford as circles, the Monterey as squares. The Eagleford carbonates have lower organic matter content, higher velocities, and lower acoustic anisotropy, while the backend argillaceous-rich samples have a wider range of organic matter, lower velocities, and much bigger acoustic anisotropy. Unfortunately, we do not have any digital images for the backend yet to interpret elements that may increase the anisotropy specifically for this reservoir. The Monterey samples have lower velocities overall, span a wide range of organic matter, and present a much lower degree of acoustic anisotropy due to the random particle orientation as well as the low matrix and inclusion moduli contrast. The velocity results shown previously were used to calculate the P-wave modulus to generate the models that will be shown next. But before we do that, let's review the definition of the bounds in the velocity model. As expressed before, elastic rock properties depend on the individual component properties, which once combined generate an upscale acoustic velocity. The end-member models for acoustic velocity of a binary mix with a low moduli host and higher moduli inclusions can be defined using the Royce and Voigt averages. On the x-axis, we will see the volume of inclusions increasing to the left, starting from 100% volume of the host. The percolation threshold establishes the point when enough inclusions are present to connect through and become load-bearing, dominating the response. The Royce and Voigt averages, in simple terms, are a series and parallel averages where either the host or inclusions dominate the modulus response. In the Royce average, that is the series average, the host is more dominant, and this bound is exact for a suspension of materials. It defines the lowest bound in the modulus. In this average, the stress is equally distributed on all components. The lowest velocities are observed on velocities normal to bedding. At the percolation threshold, the stiffest material, which are the inclusions, dominates the response, and the high bound of the modulus is determined by the Voigt average. This is the parallel or the isostrain average. This bound is appropriate for materials where the inclusion and host moduli have a large contrast. The fastest velocities were observed parallel to bedding. After defining the bounds, we need to understand the variation in moduli. This can be achieved using an effective medium model, which allows for continuous interpolation between the Voigt and Royce bounds by using an interpolation parameter L. In this model, a binary mixture of host and moduli is assumed. The differential effective medium model assumes a small volume of inclusions and makes an effective medium approximation for a single integration step. This model implicitly incorporates the critical concentration model from NER. Critical concentration and percolation threshold are the same. the parameter L is introduced to allow for the interpolation between the Royce and void bounds, as mentioned before. These bounds are retained. That is, for Royce, the value of L is 0, and for void, the value of L is 1, respectively. Inclusions are added incrementally, each at a longer length scale, until the final composition of the mixture is reached. Now let's look at where the data plots within the models. Each plot contains the calculated p-weight modulus versus the organic matter content for the 3 separate formations. As mentioned before, digital images are only available for the Eagle Ford and Monterey samples. Therefore, the organic matter volume for the backend is still under review. The twin sample sets are colored consistently throughout this presentation, where the faster velocities, parallel to bedding or VP90, are colored in red, while the slower velocities, normal to bedding or VP0, are colored in blue. The Royce and void bounds are defined by using representative host and inclusion moduli and an L value of 0 and 1 respectively. 0 for Royce and 1 for void. Approximate kerogen elastic properties were obtained from literature. The fitting parameter for the model is the percolation threshold. We will discuss the interpolation value L in detail next. The Eagle Ford carbonate and backend samples in this study are in the oil generation window and have a kerogen modulus corresponding to a mature kerogen. The Eagle Ford samples have the highest inclusion moduli and highest overall moduli values, with a percolation threshold of about 50%. Due to the uncertainty in the backend organic matter volume, the results shown here are preliminary, but they indicate a lower inclusion modulus. An assumption was made for the Monterey samples with regards to the thermal maturity, and therefore kerogen modulus. In general, the data shows lower moduli and a percolation threshold at approximately 45%. In order to understand the interpolation parameter L and vertical separation between the twin sets, or delta L, we will build some intuition by introducing the L plots next. Let's start from the simplest model examined already, which are the Royce and void bounds. In this model, the laminations or inclusions are fully connected at the plug scale, and the lower Royce bound is representative of the VP0, and the higher void bound is representative of the VP90. Let's look at more complex cases, particularly where the organic matter is not in connected layers across the sample. In this case, the void and Royce averages are no longer appropriate to represent VP0 or VP90. The preferential orientation of inclusions present in the sample will determine the level of anisotropy, and therefore delta L, as we have already seen in the Eagle Ford and Monterey samples. Longer and preferentially oriented inclusions will result in higher anisotropy, thus a higher delta L. Randomly oriented and lower aspect ratio inclusions will show less anisotropy, thus a lower delta L. So this will be representative of the Eagle Ford samples, and this will be representative of the Monterey shell samples. Finally, we look at the moduli contrast between the host and the inclusion. If we have a low contrast in the host and inclusion moduli, then our mixing rule approaches a Royce average. If we have high contrast in the material, the mixing law approaches the void average. With this in mind, an individual L value is calculated for each data point, and delta Ls are calculated. Now that we've built some intuition on the interpolation parameter L, let's look at the variation of velocity with propagation angle, and let's look at a geometric relationship for the L calculation. The variation of velocity with respect to the principal velocities can be related to an ellipsoidal variation with propagation angle theta. These geometric relationships here help us calculate L for measurements made at 45 degrees. Because we can measure simultaneously VP0 and VP45 using Metarock's equipment, we were also able to measure VP90 on twin horizontals. We're actually able to use these relationships to calculate L, where M will be measured at 45 degrees, this will be measured at 0 degrees or normal to bedding, and this will be measured at parallel to bedding or 90 degrees. Once we calculated the L's, we observed that these varied by rock type. When we use this to check for the angle of propagation, we notice that we didn't get back to 45 degrees. What this means is that our geometric relationship is lacking the vertical shear component. So what we notice is that a systematic error is observed with the predicted propagation angle being too low due to the neglect of the influence of the vertical shear velocity. VP45s are very important for the calculation of the C13 in the compliance tensor. However, they're not often measured. So we're offering here a first order approximation, which is still under progress, to calculate VP45 using L values per formation and using the existing VP0 and VP90 measurements. This is a reasonable approximation at low levels of anisotropy. However, at high levels of anisotropy, such as those observed in the backend, they're not producing an accurate response. So in the absence of VP45 measurements, this first order approximation could be obtained, and we can use it for analog values. An estimate of the magnitude of the correction is in progress. I'm now going to present to you our initial conclusions and future work. Our test of the model was successful in that a binary mixture model allows for the major features of the measured moduli to be understood. We've also observed, consistent with previous work, that increased levels of total organic carbon reduces the moduli, such as published by Verneck and Ner. Also, thermal maturity plays an important role in the magnitude of the anisotropy developed due to the conversion of the primary organic material into movable hydrocarbons and migration into the pore space, transitioning from load-bearing to non-load-bearing. The absolute magnitude of the velocity is largely determined by the modulus of the matrix. And last but not least, an estimate, a first-order approximation of VP45 may be made from the results of the differential effective medium model. Formations with low levels of anisotropy showed the best results. Our future work includes the development of the VP45 L-plot shear modulus estimate correction that was mentioned before. This will include the level of anisotropy. Also, detailed measurements of individual components to build a staged differential effective medium model for the composite material is underway. This will be using the acoustic microscope, as mentioned before. Finally, static measurements at the laminar and plug scale to build correlations between the static and dynamic properties is underway. This will be using the microindenter and the triaxial cell to build correlations between both properties. Finally, here are some of the reference of the work that we've done. Thank you for your attention, and we welcome your questions.